Greetings and welcome back. Today we're going to be looking at our third lecture on NMR, which is going to be about peak splitting. If you remember, there are three things already that NMR tells us. One is the number of hydrogen environments. Number two is roughly what those environments look like. So that is to say, kind of those environments' proximity to functional groups. We wrote that as the chemical shift. And the third thing was the integrals, which was how many hydrogens are in each environment. The fourth thing, which is peak splitting, tells us about the neighboring hydrogens, and that's what we're going to be talking about today. This is probably the most complex of the four things, and yet probably also the most useful at the same time. I'd like to begin our explanation of peak splitting by having you pause this and look at that molecule right there, which is a tribromoethane, and figure out exactly what the NMR would look like based on those three things listed on the previous slide that we've already gone through. I'll give you a couple seconds and we'll come back to that. Alright, so what you should have come up with is that we should have two environments. We've got one right here and one right there. This guy would integrate to two H's. We'll call this one on the far right environment A. It should have two H's. That should be its integral. And the chemical shift, usually we would say that hydrogen is attached to a carbon with a halogen are between 3 and 4. But notice that there's two bromines, kind of one carbon down, so that'll probably pull it up to the high end of that. So we'll say that the chemical shift is somewhere around 4. Alright, and let's look at environment B, which would be that hydrogen all by itself on the left side. Environment B would integrate to 1H. Because that hydrogen is on a carbon with two bromines, it's probably going to pull it down somewhere closer to 6. So we'll say that the chemical shift is somewhere around 6 ppm. Alright, so there's two peaks. The integrals are just the number of hydrogens in those environments. Hopefully this is nothing new. But let's go back a little bit and think about what these numbers represent and how NMR works. Remember that what we did was we put that molecule into a big magnetic field that pointed in some direction, and you had all of those little tiny magnetic fields coming from those spinning protons. Remember, each of those protons had spins. So we would have some of these guys that are little magnetic fields like that. And so here's one of my H's. Put these roughly in the same place. And some of them would be like this. Some of them would also be pointing down. But those little tiny magnetic fields that come from those hydrogens with spins are in that molecule, and they have essentially a 50-50 shot of either lining up exactly the same as the magnetic field itself, the big magnetic field, or they had a 50-50 shot of lining up exactly opposite of that magnetic field. So let's talk about what this means first in terms of the environment on the right, so for environment A. I'm going to draw this molecule out in its two possible ways. Let's do it like this. If we look at our environment A, there's two possibilities. Either they could exist in that NMR where their neighbor was reinforcing that magnetic field. So think of it as that hydrogen was spinning around so that that magnetic field lined up with your big magnetic field. Or it's also possible you'd have a 50-50 shot of that magnetic field of the neighboring hydrogen pointing in the opposite direction, basically pointing down instead. What would happen is that this would actually give us two different readings for environment A. So for environment A, where their neighboring hydrogen is adding to that magnetic field, we would see this guy show up with a chemical shift of 4 plus a little tiny bit. Because essentially, those guys are feeling a slightly stronger magnetic field than they would otherwise. Over here, though, the chemical shift for these hydrogens right here is actually going to experience a slightly smaller magnetic field because this neighboring magnetic field, to a very small extent, cancels this one out. Therefore, the chemical shift would be 4 minus a little bit. So because in a big kind of flask full of solution, you're going to have roughly 50% these and 50% these. You'll actually see two peaks for this. This environment A is going to show up, and if this is our 4 ppm, none of them are going to be exactly 4. Half of them will be 4 plus a little bit, and half of them will be 4 minus a little bit. So your peak, instead of one being one nice little peak, will actually be split into half slightly higher and half slightly lower than you would expect. This is called a split, and what we say is that this guy has a multiplicity of 2, or it is a doublet. A doublet is a fancy word for saying that that peak split in half. Half of it is up a little bit and half of it is down a little bit. If you see a peak that looks like that, what does it mean? Well, it means that the CH on which those carbons is located, that is to say, this one right here, environment A, is located next to a carbon with exactly one hydrogen. If you have exactly one hydrogen neighbor, the peak, the signal, would actually get split into half and always look like a doublet. So what I'm going to do is minimize that guy down, and I'll put it up in the corner up there. And let's consider environment B. That is to say, let's consider this hydrogen down here and what that peak will look like. So that hydrogen is on a carbon next to a carbon with 2 neighbors. That is to say, this hydrogen has 2 hydrogen neighbors. All right? Again, remember, we're looking at environment B, which is the one that I've circled in blue in all of these. And that guy right here is on a carbon which is next to a carbon with 2 hydrogens. So in essence, environment B has the 2 neighbors of environment A, and as we just discussed, environment A has 1 hydrogen neighbor on environment B. They're both neighbors to each other. Environment A integrates to 2 because there's 2 hydrogens there, but it splits once because it has 1 neighbor. Let's see what happens to environment B due to those 2 neighbors. All right, so again, going through our permutations. This guy has 4 possibilities in terms of its neighbors. Those 2 neighboring hydrogens could both be what we call spin up or augment that magnetic field. They could both be down, or there's 2 possibilities of one being up and one being down. I'll draw all those out there. Alright, so again, what we're doing here is we're thinking of the hydrogens as being little tiny magnetic fields, which they are when they're put into that big magnet because of their spin. Alright, so let's consider what would happen to this H. We said that that guy is somewhere around 6 ppm. So in the case in the upper left, this hydrogen is next to 2 hydrogens that are augmenting or strengthening that magnetic field. So the chemical shift on this guy is going to be 6 plus, again, plus a little. If they're both down, which we see right here, this guy would be 6 ppm minus a little bit. Alright, what about this guy down here though? He has 1 neighbor that is augmenting or strengthening that magnetic field, and 1 that is canceling it out. So essentially those 2 cancel each other, and therefore this guy would show up right in the center, or right at 6. And that would be its chemical shift. Likewise, in this case, this guy's going to have a chemical shift of 6, which is not going to be affected by its neighbors because 1 neighbor is up and 1 neighbor is down. Therefore, those 2 cancel each other out. But if we put all of this together, what we will find is that in a population of this molecule, we will have 1/4 of it, that's 1 out of these 4, be 6 plus a little bit. 1 of them will be 6 minus a little bit, and 2 of them will be right in the middle. So we would have a ratio of 1 to 2 to 1, 1 furthest to the left, 2 in the middle, and 1 furthest to the right. So that peak, centered around 6 ppm, would look like this. Little, bigger, little. And that is what your signal would look like for environment B. Again, it's around 6 ppm. It's going to integrate to 1 hydrogen, but instead of being a single peak, it's going to be split into what we call a triplet. A triplet has 3 peaks, all right next to each other, evenly spaced out closely, and their ratio would be 1 to 2 to 1, and that is just simply because of the probability of having two neighbors, you could have them both up or both down, or twice as good of a chance of them canceling each other out. This adds a great amount of complexity to what we see. In fact, let's consider one slightly backwards. If you see something that looks like this, that signal would be a quartet. It's 4 peaks, and the ratio is 1 to 3 to 3 to 1. What that tells you is the amount of hydrogen neighbors. So again, considering these backwards, if it's a single peak, that means that there are no hydrogen neighbors. If there is, and you can go to that last slide, if there's one hydrogen neighbor, it means that you'll have a doublet or 2 peaks. A triplet or 3 peaks means that you have 2 hydrogen neighbors. So a quartet, which is what we see right here, means that you have 3 hydrogen neighbors. So this is incredibly useful information because it not only tells you about the signal itself or the environment itself, but also about what's nearby. So let's write a little table on this. The number of neighbors, again, this is hydrogen neighbors, and we're always talking about H, C, C, H. It's hydrogens on carbons with neighboring carbons that have hydrogens. All right, so think of it, it's kind of like that vicinal situation where there's a CH next to a CH. If you have 0 neighbors, the peak multiplicity, or what that peak will look like, is just a singlet, which would just look like this. It's what we've always considered up to this point. If you have 1 hydrogen neighbor, you would get a doublet. And the doublet looks like this. 50% to the right slightly, 50% to the left slightly. If you have 2 hydrogen neighbors, it would be a triplet. And a triplet was ratio of 1 to 2 to 1, just like that. And if you have 3 hydrogen neighbors, you would have a quartet, which would look like this. 1 to 3 to 3 to 1. And this is what we would always see. And it goes up and up and up and up. Usually after that, we tend to use the word multiplet. I believe that 5 is called a quintet, etc., etc. So I'll write these out just in terms of their peaks. We don't generally use their numbers after that, but we would say that 4 would give you 5 peaks, and 5 would give you 6 peaks, 6 would give you 7 peaks, and 7 would give you 8 peaks. So this, again, there's a common mistake is that people tend to think about the number of peaks and the integrals as having anything to do with each other. They don't. The integral tells you how many hydrogens are in that specific environment. So if we were considering this guy right here, the integral would be 1 because there's 1 hydrogen right here on this peak. This splitting tells you what's on the neighboring situation. So how many hydrogens on the neighboring carbons. And that's what we're looking at right now. Let's look at these ratios. The ratios are, I would say, not necessarily of utmost importance, but it's good to be able to tell if there's multiple peaks next to each other, for instance, that you're actually looking at a quartet and not just a triplet next to a singlet. So the ratio on a singlet is, of course, just 1 because it's 1 all by itself. For a doublet, it's 1 to 1. For a triplet, which is the second one we did on that previous slide, it was 1 to 2 to 1. And for a quartet, it ends up being 1 to 3 to 3 to 1. And you could go through and draw out all of those possible situations. There would be 8 possibilities statistically, and you would see that they end up 1 to 3 to 3 to 1. But we could keep going. For 5 peaks, it's 1 to 4 to 6 to 4 to 1, etc., etc. If you remember your math, your algebra, this is actually Pascal's triangle, which is what tells us these ratios. Pascal's triangle works where you assume infinite zeros in every direction, and you basically add these two numbers together to get 1. These two together would be 0, etc. And you go through adding numbers together. If you have no idea what I'm talking about with Pascal's triangle, it's not the end of the world. I'm not going to ask you what ratios are, but I do expect you to know what those first kind of 5 look like there. All right, so let's move on and do some examples. Alright, so with this molecule, which is just 2-butanol, I'd like you to go through and see if you can work out all 4 pieces of information for each of those peaks. So the first is the number of environments The second is roughly what their chemical shift would be. The third is their integrals, or how many hydrogens are in that environment. And the fourth being what their splitting looks like. And let me remind you that splitting is only CHs neighboring CHs. All right, welcome back. Let's go through these peaks one at a time. So this would be peak A. Notice that all of these peaks are going to be different. There is no symmetry in this molecule. This would be B, C, D, and then the OH would stand by itself as E. All right, so we can put this into a nice little table, and we'll label each of these A, B, C, D, E. And let's go first into the chemical shift. All right, so of note, chemical shift, let's start at the bottom. With OH, we don't really know where it's going to be. Usually it shows up somewhere between 2 and 5 ppm. I would like you to get not necessarily in the habit of guessing that, so 2 to 5 ppm is fine. That way when we do this backwards, if you see it at 2.2, you're not surprised. All right, don't go ahead and guess anything. Just assume it's somewhere in there. We can usually find it, mostly because those guys don't split with anybody, and they'll just integrate out to 1. All right, D. D isn't right next to anything. It's kind of off by itself a little bit. I would say that it's neighboring. Right, so here's D. It's neighboring a carbon that's going to be pulled up by an OH, but not by very much. So maybe instead of being somewhere around 1, it might be somewhere around 1.5. C. C is the one, it's the hydrogen that's on the carbon directly attached to the O. Therefore, this one would be pulled up to that 3 to 4 region. So I'm going to just go ahead and say 3 to 4. You could say 3.5 or something like that. That's totally fine. All right, moving on down. This CH2, just like the CH3 over here, is not directly attached to an O, but it's on a carbon with an O. So we would probably say the high end of where we would expect that, maybe 1.8, something like that. And lastly, that guy all the way to the left, there's no reason to expect that that would be any higher than a normal CH3, so we'll just say that's roughly around 1 ppm. Okay, moving on to our integrals. Our integrals should be the most straightforward thing to figure out. You literally just count the number of hydrogens in the environment. So in A, it's a CH3, so there's 3 H's. In B, it's a CH2, so there's 2 H's. C is a CH, so there's 1 H. D, there's 3, so it's a CH3, 3 H's. And lastly, in E, you have 1 H all by itself. All right, so let's look at the splitting. Ooh, splitting. All right, and again, I used this word before. Sometimes this is called the peak multiplicity. It's just how many multiple little peaks you have there. All right, so environment A, which is the one all the way off to the left there, it's a CH3, but that doesn't matter. What we look at with splitting is how many hydrogen neighbors it has. So this CH3 is next to a CH2. Therefore, it's next to 2 hydrogens. It has 2 neighbors, and it would be a triplet. Oops. One way to think about it is each neighbor splits it once. So if you have 0 neighbors, it doesn't get split. If you have 1 neighbor, it gets split in half, and then you have 2 peaks. All right? If you have 2 neighbors, it gets split twice, and then you have 3 peaks. B, environment B, it's a CH2, but again, the fact that there's 2 hydrogens there doesn't matter to the splitting. It's got a CH3 off to the left, but it's also attached to a CH on the right. Therefore, it's got 3 H's over here and 1 H over there. It's got 4 neighbors. So I'm going to just go ahead and say that that has 5 peaks. So that guy would look pretty funny. It'd look like this. But there you go. It would have 5 little peaks, so you'd know that it has 4 neighbors. All right, moving on to C. C is going to be the most complex one. All right, splitting does not normally happen between a CH and an OH. Apparently, it can happen on a really pure sample. I have run thousands of NMRs in my lifetime, and I've never seen a splitting from an OH. So I would just go ahead and assume that you're not going to see any splitting there. All right, but this CH is neighboring a CH2. It's also neighboring a CH3. Therefore, it has 5 neighbors, 2 over here and 3 over there, because they all add up, and you would get 6 peaks on this guy. So that would be pretty complicated looking. Looks something like that. All right, lastly, well, not lastly, off to the right, we have a CH3 here. It's only next to a CH, so it only has 1 neighbor. Therefore, it would be a doublet. And would look like this. All right, and finally, we have our OH. I said before that OHs don't normally split their neighbors. Likewise, OHs aren't normally split by their neighbors. Essentially, having a CH next to an OH, they just don't see each other, right? It's like neighbors with a huge wall built in between. So that guy is usually just going to be a broad singlet. It's a singlet because they don't split each other, but OHs and NHs, instead of being nice little tiny sharp peaks, tend to look a little bit more like this. They end up being a little bit broad. All right, I'm going to go into one more kind of complex splitting in a second, but I would like you guys to try one more molecule, and we will talk about this one in class. So see if you can figure out what all of the multiplicity looks like on this one. And that's the one that we'll go through first. I'm going to very briefly go through complex splitting. It's something I want you to know about for interpreting spectra, but it is something that I will give you these values on a test so that you won't have to start from scratch. But in terms of complex splitting, all of the splitting that we've talked about previously is just CHs next to CHs on all single bonds. It turns out that that splitting always works out to the gap between those peaks being around 7 Hertz. It's a very small measurement in terms of NMR. We use ppm normally, but if you dig down you can actually find a measurement in terms of Hertz. And what that means is that it's just this gap right here between those two peaks. So on a doublet, the gap is going to be 7 Hertz. On a triplet, the gap between each of those peaks is going to be 7 Hertz. All of these are going to be 7 Hertz. And that is by far the most common thing you see at NMR. So this is going to be much more complex but much less useful than anything that we have done previously. So if you'd like to, you can pause this. I will tell you that I will only ask you about complex splitting on an extra credit question. So if you'd like to not worry about it, feel free to work on the last problem and I'll see you in class. Otherwise, if you'd like to shoot for the stars, I've got to go into a little bit of complex splitting right now. All right, so 7 Hertz is what you get from a CH next to a CH that are all with single bonds. Unfortunately, or fortunately, since it helps us get some more information, there is a different amount of splitting that you would see if you have hydrogens on an alkene. So for instance, right here, these hydrogens are cis on an alkene. Their splitting ends up being 10 Hertz. So if those guys were splitting each other with a doublet, we would actually see that the peak was a little bit wider, or the doublet was a little bit wider. In fact, you can measure that out and it would turn out to be 10 Hertz. So it's a bigger gap. Hydrogens that are trans to each other on an alkene, notice that again they're still neighbors, but they're much further apart. They give us a value of 15 Hertz. So this doublet will be even wider. That is 15. And if you're not looking for it, it'll still be relatively close on an NMR. It's not going to be an inch apart when you print it out. But it's a bigger gap, and sometimes there's a little bit of a tendency to think it might be 2 singlets. But when you have an alkene, which we can tell using our other spectroscopic methods, it's really helpful to look for this because it actually tells you where these hydrogens are located kind of compared to each other. All right, lastly, if you have two H's that are non-identical, that is to say, let's say that there is a Br down here, and maybe an OH up there. And you might give me a gotcha moment and say, haha, that's an enol, so it's going to tautomerize, so it would actually turn into a ketone, in which case you're right, but bear with me. If you have two H's that are the end of an alkene, and they're non-identical, they're going to split each other. You're going to get a split of 2 Hertz. So it's actually going to look like this. They're going to be very, very, very close together. In fact, that's really hard to tell. But that distance right there between those two peaks would be about 2. So what this does is it gives us a little bit more information, but it makes things a little bit more complicated. Because a lot of times you'll have more than just one of those splittings. So not all splittings are created equal. I'm going to minimize this and we're going to get a little bit more into it. So what happens if you have a molecule that looks like this? Let's say Cl, we'll just do vinyl chloride. Because this molecule can't rotate in 3 dimensions, well, it could spin around, but notice that the double bond can't rotate. All of these are actually going to be different environments. There's a chlorine down there on the bottom of the left if you can't read my writing. So this H right here, despite the fact that this is a CH2, this H down here is always right next to that chlorine in space. That hydrogen up here is always trans to that chlorine in space. Therefore, these two H's are going to be different. this would be A, this would be B, and this would be C. So each of these is going to be split by the other two hydrogens, but the amount of splitting is going to be slightly different. So the amount of splitting, which we usually use a J to indicate splitting, put that up there, the value between, for A, let's look at A here, that guy's going to be split by B, and it's also going to be split by C. So this peak ends up being quite complicated because it's got some splitting by E once, or by B once. It's also got some splitting by C. So we're going to have this at play, and also this at play right here, because you get splitting from both of those interactions. All right, the splitting between A and B is going to take that peak, we'll just say that this is HA, and it's going to split it into a doublet. It's going to split it into a doublet, and AB, which we see right up here, this is they are cis to each other on a double bond. That'll give us a splitting of 10 hertz. Right, so at that point we would expect it to be a doublet. But also, A is going to be split by C. The splitting there is going to be 15 hertz. So each of those guys is going to be split out 15 as well. What that ends up looking like is this, where this gap is 15 hertz and this gap is 10 hertz. You can figure out all those other gaps, but we call this a doublet of doublets. Realistically, it's going to look a lot more like this. Something like that. It's a doublet of doublets because this guy is being split once by B, which splits it into a doublet, and each of those is also going to get split once by C. Therefore, we can make this little tree. Oh, I did one of my numbers there wrong. Sorry. These gaps right here are going to be 15. I apologize. You get a splitting from A to B of 10. So this would be your splitting from A to B. Then they're also going to be split from A to C by 15. So it ends up being very complicated. All right, let's look at, but all of that, this is just the peak for hydrogen A. What is the peak for hydrogen B going to look like? Well, let's start fresh here. So if this was A, this was B, and this is C, let's go ahead and look at what B will look like. All right, B is still going to integrate to 1, but it's going to be neighboring A. It's also going to be neighboring C. So the split there from B to A, those are still cis to each other. So that guy's going to give us a split of 10 hertz. The split between B and C is going to be 2 hertz because, again, looking at those values up above, these are two hydrogens that are right next to each other. All right, so if we made this into its little tree, here's what environment B is going to be like. It's going to be split by 10 hertz, right? And that is our AB splitting. And then with our BC splitting, those are only going to be split by 2 hertz. So they're going to look like that. We've got a gap of 10 here and a gap of 2 there. This is for our BC coupling. So what it's going to end up looking like would be this. Again, it's a doublet of doublets, and you've got a gap here of 10 hertz. And these little tiny gaps would be 2 hertz. So, again, when we're really looking at the whole NMR, it's just going to look like this. And you might have to zoom in really far to even see those 2 hertz because they're so close to each other. But this is what we would see, and this is what complex splitting is. It only happens when you have an alkene in the molecule. Alkynes never even come into effect because if you had an alkyne, so let's say CH3, C triple bond CH, this hydrogen is too far away from these hydrogens to get any splitting, so we would never even need to worry about. So this is a very situational, complex situation that is going to be quite difficult to decipher if you aren't aware of these values, yet it's so uncommon that I'd prefer you put it on the back burner and spend way more time worrying about this kind of splitting, kind of the vanilla splitting, which we see 99% of the time, and a lot less time trying to work this out. So if this makes sense, great. It'll be an extra credit question on the exam. If you're not sure, don't sink a lot of time into it because I'm well aware that it's complicated, but at the same time, it's just not very common. All right, thank you all very much, and we will pick up next time by trying to put all of this stuff together. Have a good day, and I'll see you soon.